In the previous lecture, we talked about how to compute the element stiffness matrix and the element load vector entries for the linear approximation of the boundary value problem that we had taken. We discussed in detail how at the same time, while we are doing the element calculations, we can also compute the contribution from the non-homogeneous Neumann part of the boundary. Okay, that's all that we have to consider as far as the contribution of these boundary fluxes or tractions. Okay, then we now have the element stiffness matrix and the load vector as we had constructed in the previous lecture. So we have for an element the stiffness matrix k tau and the load vector f tau. Next, the question that we had asked in the 1D problem and which we will ask again is, where do we assemble? Where to assemble? That is, in the global stiffness matrix K, in the global problem Ku is equal to F, where will, which row and which column should I add the entries of the element stiffness matrix, and similarly for the load vector. So for this again we have to have a local to global enumeration. Okay, for which we had defined for the 1D case the construction of an Ieldofs array or Ieldofs vector. Okay, so what we can do is either we have it as a array or as a vector, but we will choose here to have this Ieldofs as a vector. Okay, now in every element we will have end of element number of degrees of freedoms. Okay, for us, for the 1 p equal to 1 case, that is the linear approximation, end of L is equal to 3. So our job is essentially to find the local to global enumeration for 3 degrees of freedom at the element level. Let's take again our first element in the domain that we had made in the previous lecture. Okay, now I will talk of the degrees of freedom as this. So this is tau equal to 1, this is the global node 1, global node 2, and if you remember, this is the global node 5. And we had said when we do the local enumeration, this is 1, this is 2, this is 3. Okay, remember, local enumeration is always done in a counterclockwise manner. So how do I pass this information to my assembly routine? That is, how do I tell that okay, the local one corresponds to the global one? This again I can do while we are making the mesh, while we are making the nodes of the elements. So in this case, it's quite simple that we see that as we are storing the names of the nodes for the element in the nodes array. Okay, similarly, I can give the same numbers because the global degrees of freedom are also numbered the same way as the nodes because they correspond to the nodes now. Okay, we can give the same numbers to the Ieldofs. And how will I do the Ieldofs numbering? So Ieldofs, so for an element, for element IEL. Okay, in the Ieldofs, the starting point will be start at, you have your end of L into IEL minus 1 plus 1. For the element there are end of L degrees of freedom. So for the element the degrees of freedom for the element correspond to, now the end one corresponds to end of L into I E L. Okay. So these are the locations in the Ieldofs array which are going to give me the first degree of freedom corresponding to the element and the last degree of freedom for the element. For example, if I go by this, then Ieldofs, I will say 1, because for the element 1, IEL minus 1 is 1. This is the first location, will be equal to the correspondence of the local 1 with the global number. So I will put the local 1 is equal to the global 1. This is the global number, this is the local. Okay. Similarly, Ieldofs 2 for the element will be equal to the global 2. Ieldofs 3 for the element will be equal to 5. So Ieldofs 1 to 3 correspond to the degrees of freedom of the element 1. Now I go to element 2, for example. If I go to element 2, here I will have for the element 2 you will also have 4 as a degree of freedom, and this is the, for the element 2 this will be 1, this will be 2, this will be 3. Okay. So for the element 2 I will have the Ieldofs, the starting Ieldov corresponds to 2 minus 1 is 1 into 3 plus 1. So the Ieldov 4 will be the first local degree of freedom for element 2, and this will correspond to the global number 5. Ieldov 5 will correspond to the second local degree of freedom of the element 2, it will correspond to 4. And Ieldov 6 will correspond to the third local degree of freedom of element 2, and it will correspond to 1. So you can imagine that I have these blocks. This is for tau equal to 1, this block is for tau equal to 2. So this way I can arrange the entries of the Ieldofs array, Ieldofs vector, and this can exactly tell me what is the enumeration, what is the correspondence of the local degree of freedom with respect to the global degree of freedom. Okay. So then using this information, what do I do? So now I start for each IEL, I start my assembly loop for each element IEL. Okay. Okay. For I is equal to 1 to end of element. This is the local I. I will find the global I. This is equal to IEL DOFs. I will have for the element IEL, I will find here the I first is equal to, okay, n of L into IEL minus 1 plus 1. Okay, I last is equal to I first plus end of L minus 1. Okay. So I find exactly where in the Ieldofs array the degrees of freedom corresponding to the element are sitting. So then I will come here and I will be equal to I first plus I minus 1. So you see the I equal to 1 will correspond to the Ieldofs sitting in I first plus I minus 1. Okay. So then I will do F. I will now assemble the global I F. remember that before doing the assembly, these the F and the K matrices should be initialized to 0, which is equal to Fi plus F for the tau I. Okay. Now embedded loop for j is equal to 1 comma end of L, big J is equal to again Ieldofs I first plus j minus 1. So this gives me the global name of the jth, the column degree of freedom, and then I will have k I comma j is equal to k I comma j plus k tau I comma j. So this is all. As far as the assembly is concerned, we are now able to assemble the stiffness matrix and load vector corresponding to the element. So I now end the loops. So you end the loop over the rows, over the columns and rows, and over the elements. So this is all that I need to do as far as the assembly is concerned. What is left now? What is left is application of Dirichlet boundary conditions. So application of Dirichlet boundary condition. Okay. So here this corresponds to IBC type is equal to 1, which is the Dirichlet homogeneous Dirichlet. Let's see our numbering. Okay. So we will have the 1 and the type 2, which will correspond to our element. So here I will have either this or 2. This is the non-homogeneous Dirichlet, non-homogeneous, and this is the homogeneous Dirichlet. Both these have to be enforced in our global stiffness matrix and the load vector. So how do I find out which are the degrees of freedom which have to be fixed? So again I will draw the simple domain that I had taken. I will write the global nodes and the degrees of freedom, and I will remember that this was edge 1 on which I had IBC type 2. That is, this is the only edge where the Dirichlet boundary conditions had to be applied because u was equal to 0 on this edge. So now the question is that if I have to apply the Dirichlet boundary conditions on this edge, that is, I have to fix the displacement u along this edge to be equal to 0, then all the degrees of freedom sitting on this edge have to be made equal to 0. So how do I identify those degrees of freedoms? Easy. When we are finding the neighbors of the sides, when I go to element 2, for example, I find that the second edge of the element is sitting on the boundary segment 1. So I immediately know that okay, for this, when the for the boundary segment 1, the boundary condition is of a Dirichlet type, which is actually it's a homogeneous Dirichlet type. Sorry, it's not a non-homogeneous, it should be 1. Boundary type should be 1. IBC type should be 1. Okay. So here, as soon as I do that, I find that okay, this is an edge on which the Dirichlet boundary conditions have to be applied. So as I loop over the elements to find the neighbors, when I am finding the neighbors after making the mesh, then immediately I can also make a list of the degrees of freedom which are lying on the boundary. To make the list of the degrees of freedom lying on the boundary, I go to the particular edge, okay, which is the second edge of the element, and I say okay, tell me which are the degrees of freedom which are non-zero, which are active on this edge, and I find that for this edge, degree of freedom, the local degree of freedom 2 and the local 3. So if I draw the second element, this is the local 1, local 2, local 3. These are the ones which are lying on this edge. So these are the ones which have to be fixed. So immediately I start a counter and I start counting the number of degrees of freedom which have to be set to 0. So I will say that I will put start total number of fixed degrees of freedom is equal to 0, initialize. Now I loop over these edges and I said I have name of the fixed node, I increase the counter. So for example, for the first one will be equal to the global node 1. Name of the second node which is fixed, from this element it comes out to be the global node 4. Okay. Then I go to the other elements, and as I am doing this assigning of the degrees of freedom and assigning of the neighbors on the edges, I come to element, so this will be element 5, this is, I come to element 6. When I come to element 6, I find again that element 6 is sitting on boundary segment 1, which has a boundary type 1, which means that here also the displacement conditions have to be satisfied. Now I come to this one, so my counter would have become 2 at the end of the element 2, assembly of element 2. Okay. Now when I come to element 6, I check whether a degree of freedom which lies on a fixed edge of this element 6 is already accounted for or not. So I find that okay, this element 6 has again its second edge on the boundary, and that has degrees of freedom, global degrees of freedom 4 and 7 as the fixed degrees of freedom. But then I find that 4 is already accounted for. Then I go and say that, so if it is accounted for, I don't add it again, but then I find 7 is a new degree of freedom, so I say this is equal to 7. So now I have, this counter has become 3. So I know that there are 3 degrees of freedom which have to be fixed coming out of the Dirichlet boundary conditions, and the name of these degrees of freedom are this. And while I am giving the naming, okay, at the same time I look at the type. Okay, so I can find the value of the fixed degree of freedom. See, you need not have only 0 boundary conditions. You can have a fixed displacement or a fixed temperature which is non-zero on the edge. So I will say that okay, the value of the first fixed degree of freedom comes from the information given for this boundary edge as far as the temperature is given. In this case it is 0. Similarly, I will have the value of the fixed degree of freedom on the, for the second degree of freedom is also 0, val fix for the third degree of freedom is also 0. So I know exactly which degrees of freedom have to be fixed by this numbering here, and I know exactly what is the value that has to be given to it. So all this information is available to me. Now what do? I go to my global stiffness matrix, okay, and then so I start loop, that is loop over I is equal to 1 to n dot fix, that is the total number of fixed degrees of freedom. Find name of the degrees of freedom is equal to, from what we have given in the previous slide, okay, it is name fix I, it is name fix I, val is equal to val fix I. Okay, so I know which global row I have to go to, and I know what is the value. Okay, then after that, what do? I will simply say that k named of comma named of is equal to 1. Okay, then k named of comma j is equal to 0 for j not equal to named of. So what have I done? I have gone to this particular row which corresponds to the given degree of freedom, global degree of freedom, and I have made the diagonal entry of that row equal to 1, and all the off diagonal entries of that particular row equal to 0. Okay, so once I have done that, then this row is taken care of. Then f named of is given the value which is the fixed value. Sorry, it's actually val only. I have given it a name, so it's val. Okay. After this, what do I have to do? I have to also correct the remaining equations. So in the remaining equations, what do? F j is equal to f j minus k j comma named of into val. So what am I doing? I am going to the other equations and accounting for the known value of the given degree of freedom by taking the multiple of that corresponding column entry against the known value of the degree of freedom to the right hand side, because this is now a totally known quantity which modifies my load vector. Okay, and then after that I go and say k j comma named of is equal to 0. Okay. So once I have done this, then I end the loop. Once I have done this, what have I done? I have taken care of the degree of freedom in its corresponding row by fixing it, by modifying the stiffness entries in such a way that it gives me the desired value exactly the same way as we had done in the 1D case. And then we went and first modified the load vector in the other rows to account for the known value of the degree of freedom that we are trying to eliminate from the system, and then set the corresponding row entry to 0. So once I have done this, now the Dirichlet boundary conditions are also taken care of. Okay. So once you see that when the val is equal to 0, that is, I am talking of a homogeneous Dirichlet condition, then really this quantity leads to no correction on the right hand side. But we have written it in a generic way so that this can be used for all types of homogeneous and non-homogeneous Dirichlet boundary conditions. But one thing I would like to point out again is that, remember, we are applying the boundary conditions on the edge and not only at the nodes. There is always a misconception that the Dirichlet conditions have to be applied at the nodes and that the force conditions have to be also applied at the node. We are doing integrals along lines, along edges. Those integrals actually translate to fixing of values or assigning of loads to the degrees of freedom sitting on the particular edge. This is something that we have to always keep in mind. Okay. So now we should be able to solve the problem. Okay. If I look at this, if I look at the fifth equation, that is the equation corresponding to the global 5 degree of freedom, this equation will have contribution from elements 1, 2, 4, 5, 7 and 8. Okay. So really it has contributions from 1, 2, 3, 4, 5, 6 elements, because there are 6 elements which are sharing this node amongst themselves. Okay. Similarly, if I am talking of the third node, this will have only contribution from the third element. No other elements actually participate in this node. So you see that I can have contribution to a node coming from 1 element, from 2 elements, from 5 elements, from a varying number of elements. It is not the same as what we had in the 1D case, where at most 2 elements participated in the equations for a node. Here we could have, depending on the mesh, many more elements present. Another thing, if I look at this degree of freedom 1, if you remember, this degree of freedom actually participates in the equations, actually in the definition of u along this edge, along the boundary edge 2, as well as along the boundary edge 1. Okay. When we say that we are going to fix the u on an edge, that forces us to fix the value of 1, of the degree of freedom 1. In this case, the value of degree of freedom 1 is actually equal to 0. Okay. So this, the Dirichlet condition actually predominates over the Neumann condition. That is, the value of the degree of freedom, if it is fixed from one side, then that is what we are going to assign to that particular degree of freedom. And we should not confuse that, okay, from one side I am getting a load contribution, from the other I am getting a displacement contribution, because remember, these things are defined only on the edges. Okay, so with all this done, we should now be able to assemble the global stiffness matrices, the global load vectors, apply the boundary conditions, the Dirichlet boundary conditions, and solve the problem. Okay, so that should not be a problem as far as the simple problem that I have taken. Let me ask another question. I have a domain like this, let's say, okay, with, I could also have an internal cutout. So first let's make a simple mesh over this. So if there is a cutout here, you could easily make, I am making a very crude mesh, simplest possible mesh of triangles that I can make. Okay, so your first job is always to make the mesh. Now before making the mesh, implicitly what have I done? I have identified the geometrical entities. That is, this domain has these distinct edges, edge 1, edge 2, edge 3, edge 4, edge 5, edge 6, and the 4 internal edges which correspond to the boundary of the whole. So it has actually 10 such edges. Okay. Now here I have not done anything as far as the loads are concerned. So let's say that I have, here I am fixing this specimen, here I am applying a traction, here in this region also I am applying a traction, okay, and I may be fixing it in this region. So as far as the definition of the geometry was concerned, you see that I needed only definition of these 10 edges. But as far as the boundary condition is concerned, this edge has one boundary condition specified, which is zero flux. This has another boundary condition applied. This edge has another condition. This one has another. This one has another. And you see this edge has a different boundary condition, while this edge has a different one, and this edge has a different one. So and all these edges also have their specific boundary conditions applied. So actually an edge, a global geometric edge, may have subsections where boundary conditions are changing, and we have to honor this transition or change of boundary conditions by putting nodes at those points where the boundary condition transitions. So this mesh is actually unacceptable, because here is a point where the boundary condition transitions, okay, and I have not put a node there. So in a very simplistic way, I should have a line like this, okay. So I am just simply dividing the mesh, okay? And if I have this line, then I will have to now mesh it like this. Okay. So there are times when, in fact this is always going to be the case in practical problems, that the boundary conditions decide how many boundary segments we are going to define a priori, and from there we have to first honor the existence of this transition of boundary conditions while putting nodes. So this has to be a node, this has to be a node, this has to be a node, this has to be a node. All these have to be nodes, because the boundary conditions are transitioning, as well as in certain points the geometry is transitioning. For example, here the boundary conditions are similar, but the geometry has a change. So I have to honor those. These nodes I have to put. So these are the minimum number of nodes that I have to put in the definition of our mesh. Okay. So the new mesh is no longer what I had drawn earlier, it is actually these entities. Okay. So in most problems, one has to be careful that we do not violate the applied boundary conditions. Now another thing I may have is I may have different material domains. Nobody tells me that my two-dimensional domain will have the same material everywhere. So I could have absolutely different materials in different regions. For example, I take this sample, I decide to put one material here, one material here, and something else here. Okay. So these material boundaries also have to be clearly honored when we are talking of making the mesh. Okay. So these nodes, in fact, demarcating these material boundaries have to be also put, and while we also have the other ones corresponding to geometry, and then depending on the boundary condition, for example, here I may have a traction applied or a flux condition. So this point also has to be a node. I may fix this part, so this guy will also have a node here. So we will have to have these nodes put a priori as soon as the boundary information, material information, and the geometry information is available to us. Then we start meshing. The rest of the mesh can come after this. So these things have to be kept in mind. Okay. Now we have done enough with these linear approximations. We have gone through the whole process of what we will actually be doing in a finite element setting. The only thing which is missing in what we have done is that the integrations have been done in an exact way. We would like to add numerical integration, which we will talk about later. But first, who tells me that linear approximation is all that I need to do? I may have to do better than linear approximation to get a reasonably accurate solution. Okay. So if I have to do better than linear approximation, I should be able to make higher order approximations. Okay. So when we are talking of higher order approximations, remember that again we will be talking of these piecewise polynomials. So the issue of completeness, the issue of linear independence, all these issues will have to come up. So as far as 2D is concerned, the higher order polynomials are given. See which monomials have to appear in a given polynomial, which all the monomials which have to appear in a given order polynomial for that representation to be complete is governed by something called the Pascal triangle. Okay. So what do? If I take a monomial corresponding to the 0th order polynomial, it is 1. If I now take a monomial corresponding to the linears, it has x and it has y. If I now take, so this corresponds, 1 x y are the monomials corresponding to linears. If I take quadratic, I will have x squared, xy, y squared. If I take cubic, I will have x cubed, I will have x squared y, I will have x y squared, and I will have y cubed. Okay. If I am talking of 4th order, then I will have x to the power 4, x cubed y, x squared, y squared, x y cubed, and y to the power 4. Okay. So constant monomial order 0 polynomial will require only one monomial in its definition. So this is order, we will call the order p equal to 0. Linear approximation or the linear representation will require 3 monomials, 1 x y. A quadratic representation will require 6 monomials. All the things which lie above are also included. 6, which is 1 x y, x squared xy, y squared. A cubic will require 10 monomials. That is, to all that which was there for the quadratic, I add x cubed, x squared y, xy squared, y cubed, and that is 10. And a 4th order will, cubic is, this is cubic. 4th order will require 15 monomials in its definition. Okay. So when we are talking of construction of bases, when we talked of the linear, we saw that we had 3 bases, so we were fine, and that the basis was linearly independent and complete. So when we go to the quadratic approximation over a triangle, we actually need to have 6 basis functions defined in the element. Okay, that is 6 independent functions of degree 2 have to be defined, of degree up to 2 have to be defined in order to completely represent a quadratic polynomial in the element. So how are we going to do these things? You see, cubic will require now the 10. The generic definition is that the number of monomials corresponding to a given order of representation will be equal to the number of monomials is given by p plus 1 into p plus 2 by 2. You see that when p equal to 1, this is 2 into 3 divided by 2, which is 3. P equal to 2, this is 3 into 4 divided by 2, which is 6, and so on. So you will get exactly out of this the number of monomials or independent bases that have to be defined in order to completely represent the given order polynomial. Okay. This has to be used in our definition of, or in our construction of these higher order basis functions. So okay, if I take, so now I am going to operate in the master element only. So let us take the generic master element. This is psi, this is eta, and I am going to make the element like this. So we have made the generic master element tau hat. Okay, I am not going to write tau hat here. Now, as far as the linear approximation was concerned, I had the basis functions defined with respect to these 3 nodes. When I want to do quadratic, I will borrow a lot of ideas from what we have done in 2D. Why? If I am taking a quadratic approximation in this triangle, then the projection of the quadratic on the edge, okay, because it's a quadratic in a triangle, so the projection of the quadratic on, let's say, the first edge should also be quadratic. If the projection of the quadratic on the first edge is a quadratic, I have the basis functions on this edge defined with respect to the corners. Then the simplest way I can define a quadratic on the edge is put a middle node here. Okay. Similarly, I look at this edge. On this edge, I know that the quadratic defined over the whole triangle, when I look at its projection on this edge, it also has to be a quadratic. So why not define a middle node here? Okay. Now what we do is we draw the line parallel to the base through this middle node, and the line parallel to the base through this middle node. This will cut at the middle of this edge, and as we have said for these two edges, similarly on this edge also the quadratic, the projection of the quadratic should be a quadratic. So this edge also requires a third edge node to be added. So you see that in order to have the quadratic, at least on these edges, we have to have these 3 new nodes added. So why not go ahead and add these 3 new nodes? Okay, then I'll complete this element. Okay, so I have, now you see 1, 2, 3, 4, 5, 6. So I have 6 such nodes. Now the question is, can 6 is the number of independent basis functions that we require to define a quadratic approximation? Okay, we have 6 nodes. Now can we define a basis function or a shape function in the element, okay, such that these shape functions, these 6 shape functions, correspond to a value 1 at a node, that is their corresponding node, and 0 at all other nodes, and they form a complete basis for the quadratic. So our challenge is, let's say I want to now define n1. So I'll call this node is 1. I will do the numbering in a way which is a little different from the standard. 1, 2, 3. This is 4. This is 5, and this is 6. Let's say, if I now want to define n1, n1 will be such that it is 1 at this point, okay, becomes 0 at this point, and 0 here. Similarly, on this edge it is 1 at this point, 0 here, and 0 here. So n1 is a curved roof, okay, which gradually dies off to a value 0 on this second edge of the element, okay, on the second edge of the master element. How do I now define a quadratic which is 1 at this point and 0 at along all these points, that is along this edge and at these points? It's quite easy. You see that if I take a function which vanishes along this line, then multiply these two functions, I should be able to get a quadratic. What is the equation of this line? The equation of this line is, if I take the equation of this particular line, it will give me psi plus eta is equal to half, because this corresponds to the point half 0, this corresponds to the point 0, 0, this corresponds to the point 1, 0, this corresponds to the point half, this corresponds to 0, 1, this corresponds to 0, half. So you see this equation of this line is psi plus eta is equal to half. Okay, equation of this line is psi plus eta is equal to 1. So now if I define my new, if you see that n1 hat is a function of sine eta is equal to some factor alpha into 1 minus psi minus eta into half minus psi minus eta. Okay, then this function, if I multiply these things out, is going to be a quadratic and in sine eta, and also it is going to vanish along this line and this line. So if it vanishes along this line and this line, it is vanishing at all these nodes. Okay, so this is a very simple way of defining n1 hat. Alpha will come by putting the value of psi eta equal to 0 because I want the n1 hat at 0 0 equal to a value 1. So what will I have if psi eta is equal to 0? So n1 hat at 0 0 is equal to alpha into half, implies is equal to 1, implies alpha is equal to 2. Okay, so I can replace alpha with 2. That is my definition of the quadratic shape function corresponding to the node 1. Similarly, if I want to define the quadratic shape function with respect to node 2, okay, such that this quadratic vanishes at all other points. Okay, so you see that all other points lie on which lines? They lie on this line and they lie on this line. Okay, so if I take the equations of these two lines and multiply them with the factor in front, that should give me the equation of the second the representation of the second shape function. Okay, so now equation of this line is psi is equal to 0. Okay, so let me go ahead. Bottom line is that all these functions can be constructed in terms of products of the equations of one of these lines that I have drawn. Equation of this line is eta equal to 0. Equation of this line is eta is equal to half, and equation of this line is psi is equal to half. So I take, as far as n2 is concerned, I will take psi into 1 minus psi minus eta into alpha. So you see that so n2 as a function of sine eta is equal to psi into 1 minus psi minus eta into some constant beta. Now where should n2 be? If you check that this thing will vanish on all the other points. At the point psi equal to half, eta equal to 0, this is equal to half into 1 minus psi minus eta, which is half, into beta. This has to be equal to 1, implies beta is equal to 4. Similarly, if I, so this was not my n2, this was my n4. Sorry, I should go back and change this. This is my n4. I want to now have representation of n2. n2 is one which should be having a value 1 at this node and 0 at all other nodes. If it has to be 0 at all other nodes, I can make that happen by taking this function to vanish on this edge and this edge. Okay, what is the equation of this edge? Equation of this edge is psi is equal to half. Equation of this edge is psi equal to 0. So I can define n2 hat. So this will be n4. n2 hat as a function of sine eta is equal to psi minus 0 into psi minus half into gamma. Okay, this thing should have a value 1 at the point psi equal to 1, eta equal to 0. This is 1 into half into gamma. This is equal to 1, implies gamma is equal to 2. So this way I can construct all the shape functions corresponding to the quadratic. Okay, let me do further this thing. How will I do n5? So I found n1, I found n4, I found n2. Okay, let's do n3. n3 is one which vanishes if I see along this edge and this edge. So n3 will have equation eta minus half into eta minus 0 into some constant. That constant I can find by putting the value of n3 equal to 1 at the node 3. Okay. Similarly, n5 is one which is 1 here and 0 at all other nodes, which means 0 along this line and 0 along this line. So I take the equation of this line, which is psi equal to 0, and this line, which is eta equal to 0. So this one is psi eta, and so on. n6 is very easy. n6 will be 1 here, 0 along this line and this line. So it is 1 minus psi minus eta into some constant that is equal to n6. So this way I can construct the quadratic shape functions, all the 6 quadratic shape functions. And what I have done is essentially an extension of the Lagrangian definition to 2D. So in the next lecture I am going to extend this further to the cubic approximation, to the 4th order approximation, and then we will go and look at some more families of shape functions, okay, that can be used in our practical problems.